I think our screen is visible to you all, right? Oh, you want video? So our screen is visible to you all. I mean, the screen is shared to you all. Yes, sir. Okay. Uh, if you want, I can open also. Okay. Let me open something. Yeah, you can start, please.
Okay, so I'm starting here. The remaining part of the first module. Okay. It's got by full screen. Am I audible?
Yes, sir. Yes, sir.
Okay, so let's see what. So now you are allowed. You are allowed, and you can access the same. So whenever there is problem, please tell me, because I can't get the information. So the remaining part of the first module, which we did up to here, the determination of the magnetic moment with the help of the simple Bose-Stoner equation, mu is equal to root over n into n plus 2 is this is an important part in order to calculate or find out the magnetic moment. The foremost point and the first point is that you need to first write down the electronic configuration according to the crystal field splitting. So what we find here in this case, the for titanium Cl36H2, for this what we do, first we calculate the value of unpaired electrons in the metal. Then titanium 3 plus means it is a D1 system. So we get the number of electron as here, keeping only one electron. And so the value is root over 1 into 1 plus 2. So it becomes 1.73. Similarly, when we come for the MnF26H2O, the MnF2 means Mn has a plus 2 oxidation state. It is a D5 system. So for this, we have got this 5.9. So in this way, you will have to calculate all the different things. Now, let's take some examples. Say for cobalt En3, cobalt En3 3 plus. Cobalt En is known as, it is a ligand known as ethylene diamine. Ethylene diamine. Okay, abbreviated form is En. Now, ethylene diamine, it is a strong field ligand and it always gives rise to a so cobalt 3 oxidation state is plus 3, so its number of electron, it is a d6. Now, when a strong field ligand is there, then definitely there will be some low spin complex. So in order to get that low spin complex, what will be the first? You will have to first you will erasing. I don't know why. Just 1 minute. Let me draw it again. So there are 6 electrons in it. We will fill up with 6 electrons, but as it is a strong field, so all the 6 will come here. That means there is no unpaired electron. So the value of magnetic moment for this will be mu is equal to root over 0 into 0 plus 2 is equal to 0. So it is a diamagnetic. Okay, now the molecules, like if I take the molecule cobalt F6, say K3 cobalt F6, that is your ion is cobalt F6 3 minus, cobalt F6 3 minus. So here cobalt is also in +3 state. So it is a D6 electronic configuration, but fluoride is a very weak field ligand. So it's So being a weak field ligand, it will give rise to a high spin complex. Okay, so its initial electronic configuration was like this: 1, 2, 3, 4, 5, 6. Right now it is 1, 2, 3, 4, 5, 6. So there are total 4 unpaired electrons. So in this case, mu is equal to root over 4 into 4 plus 2 is equal to 4.92 Bohr magneton. So it shows that with the same metal in same oxidation state, depending upon the nature of the ligand, whether it is a strong field ligand or a weak field ligand, the magnetic moment changes. And that is due to the filling up of the orbitals splitted after the splitted under the crystal field. So this is an important part which can be discussed, which can come into the exam. Our next one important feature is that a special molecule, some kinds of, we know that the usually the molecules are divided into in the magnetism there are 4 types: paramagnetic, first of all, then diamagnetic, then ferrimagnetic, then ferromagnetic, ferri, and also antiferromagnetic. Now, you do not need to study all these. Your concern is here paramagnetic and diamagnetic. And in a special case, some example of antiferromagnetic will be discussed. The antiferromagnetic has the magnetic moment less than paramagnetic. Okay, its mu of antiferromagnetic is less than paramagnetic. The most important example or the first elucidated mechanism for the antiferromagnetic observation in the molecular magnetochemistry was for CuOAc whole 2 dot 2H2O dimer. This molecule, it has a magnetic moment of mu is equal to 1.43. But we know that copper 2 is a D9 system with 1 unpaired electron. So for 1 unpaired electron, expected or mu spin only will be root over 1 into 1 plus 2 is equal to 1.73. But the observed magnetic moment is 1.43, that is less by an amount of 0.3 Bohr magneton. So what is this? So this is an example of antiferromagnetism. Now this antiferromagnetism may be how it can be described with the help of different mechanisms. We can discuss it right now. Suppose in order to understand the antiferromagnetic coupling of the electron spin, we need to draw the structure first. Copper acetate So it is something like this, where this one, where this one is CH3 COO. This means it is a acetate ligand. Okay. Okay. So here what happens after the analysis, it has been observed that so it has one unpaired electron here because this is a copper 2 system. This is a copper 2 system. So one unpaired electron is there on each of the copper ion. So there is one and there is one. Now during the when they are connected by this bridging, the electron over the top copper atom, it can come in this way and reach here. Okay. Similarly, this electron in this way can reach here. Therefore, there are four different possibilities with this kind of exchange of electron, and this causes what happens if this electron goes to this copper center, then the electrons are paired up. That is no dipole moment, no magnetic moment. So number of unpaired electron becomes 0 in that case. But this kind of transfer or exchange does not take place to 100%, so that it has certain amount, a mixture of unpaired electron over each copper atom as well as the paired up electron over each copper atom. So due to that, the amount of the magnetic moment mu value is 1.43, which is less than the expected value of 1.73 Bohr magneton. Okay, so this is a very nice example of antiferromagnetic interaction or the antiferromagnetic coupling of the copper 2 diacetate. I have made one mistake over there. This should be 1 water. Okay, please note that the 2 is on the outside. Each copper is connected with 1 water molecule. So our next topic, you can say, is so I am starting the electronic spectra of transition metal complexes and their color. Color of the transition metal complexes. For any system, we know we can draw the molecular orbital of everything in this universe as it is possible to draw a molecular orbital, and that means the energy levels, so that some of the levels are filled with the electrons, and at some level the number of total electron has been exhausted, and before and next to that there is an empty orbital. So this orbital here we can call this we can call this orbital as we can write it as highest occupied molecular orbital HOMO and the lowest unoccupied orbital. So this is lowest unoccupied molecular orbital. So when some light falls over the HOMO, then an excitation of the electron takes place from HOMO to LUMO or to the other higher levels. It is also possible if the higher energy light is absorbed by the inner orbital electrons, they can also be promoted to the higher energy levels. So this kind of electronic transition takes place depending upon the energy of the light. It means that when we talk about some electronic transition, that is then corresponding to this energy difference, delta E, it has a particular wavelength of light lambda is observed for a particular transition. For the transition of electrons between two levels, one particular wavelength light will be absorbed out of the whole spectrum of the same radiation. If this light falls within the range of the UV and visible, particularly the visible range, then it generates a color. Suppose whatever be the light, UV or visible, if this lambda, suppose now I am drawing this. The Vibgyor spectrum. Okay, this is the visible spectrum. It starts from the lambda at 400 nanometer, and this is at 780 nanometer. Now, depending upon this lambda, if the energy of separation is high, if the value of delta is high, then a light from this region will be absorbed. From this region will be absorbed for the, so this is a high energy light. Okay, so when delta E is high, whereas in the other case, if the delta E is less, then the light from this energy will be absorbed, that is delta E is less. Whatever light is absorbed, except that color, the rest of the color forms a complementary color or complementary light. That color is reflected and we observe that color. So the complementary color is, we can write it as complementary color or the actual color for any molecule. Complementary color is equal to, we can say white light, that is the composition of all the 7 lights, all the 7 wavelength lights minus the light absorbed. Therefore, if the delta is high, we will see a color, complementary color, except that high delta E. So if a violet energy or violet or indigo light is absorbed, then we will see a orange or red color. Alternative and vice versa. So the color of any system depends upon this delta E, we can say. Now the amount or magnitude of this delta E is very can be convinced very well with the help of the crystal field theory. We just need to draw the proper crystal field splitting and then assign or arrange the electronic configurations, the fill up the orbitals with the electrons, and then we can see that depending upon the ligand strength. So from here we see the color. Now the question is that why suppose water or benzene are colorless? Color for the molecule is only observed when the absorption takes place in the visible region. If it is outside the visible region, it may be a UV region light or it may be a IR region light. In either case, that will be colorless. That's why water and benzene or the most of the organic compounds, they are colorless in nature because their absorption takes place in the UV region. Okay. So if I get some example like this, then the fact will be very clear. Suppose aqueous solution of octahedral cobalt H2O6. We are taking two molecules here. One is cobalt H2O whole 6 2 plus, and another is cobalt Cl4 2 minus. Now you see both of them are in cobalt is in +2 oxidation state, so their electronic configuration is same, that is D7. In either case it is D7, it is also D7. Now cobalt H2O whole 6 2 plus, it will, if I draw the electronic configuration, suppose I am taking the cobalt degenerate state. Now in the octahedral field they are splitted as, and in the tetrahedral field they are splitted as. So in this case, for the D7 cobalt H2O whole 6 plus 2, the still the electronic fill up will be, that is of high spin 1 2 3 4 5 6, and here obviously this is high spin 1 2 3 4 5 6. For both of them, you see, for both of them the pattern is same, electronic filling pattern, but we know that the delta OH, that is this value, this is delta OH, and this value is delta TD. And what is the relation? Delta TD is equal to 4/9 delta OH. That means less than half. The amount of splitting for this one is less than half than the other one. So that's why the energy difference in the tetrahedral case is less. Energy difference in the tetrahedral case is less. Now this is pink in color. This is its color is pink, here cobalt H2O6 is pink, and the cobalt Cl4 minus 2, it is blue. Okay. So what is pink in color here? The octahedral one. That means pinks will come. Pink will come somewhere here in this region. Red, orange in this region. So for this, the energy is absorbed from the high-end region, from the violet indigo region. That's why its color will be more or less grossly it is on the opposite side of the Vibgyor spectrum, because its splitting or the delta O value is higher. That is the delta E here for the required for the transition. But in the tetrahedral case, as the energy difference is less, so as the energy difference is less, the absorption will take place from the orange or red region, and its color will be, it is deep blue in color. Color will be somewhere here. Okay, so we see that for the we can say that usually for the tetrahedral molecule, for the same metal ion, same oxidation state, and if they have comparable ligand field strength, the tetrahedral geometry will have the color towards the violet, indigo, blue region, whereas for the octahedral, the color will be yellow, orange, red, pink region. So this is the observations which has been explained with the help of the crystal field theory. So this explains how the color chemistry developed for the crystal field theory. Now there are several examples. You go through the note, you can see that. Okay, nickel H2O6, the green color of nickel H2O6 turns blue when ammonia is added due to the formation of nickel ammonia whole 6, 2 plus. Ammonia is a stronger field ligand than water. So the extent of the magnitude of the splitting will be increased here. Now another example, usually the zinc complexes are colorless.
सर उधर खुला है उधर खुले देखते हैं उत्तम के पास चाबी
सर
हाँ निकल हाँ तो उत्तम के पास टिकट से निकल
okay. So usually you will see that zinc complexes are colorless. Zn complexes are colorless, and as well as Mn2 plus and Zn2 plus, these complexes are colorless. Why? Because Mn2 plus, they have the electronic fill up of like this, which will come. Okay, I am considering that in the next stage. Just 1 minute. Okay. So our next topic is the selection rule. For electronic transitions. Selection rules for the electronic transitions. Now, suppose there are not under every condition there will be an electronic transition. The electronic transitions will take place only if certain conditions are maintained. Those conditions are known as the selection rule, which are of two types. Number one is the spin selection rule. And number two is Laporte selection rule. Out of which spin selection rule is more powerful. Spin selection rule says that electronic transition will take place only if the change in spin delta S before and after the transition is 0. Only under that condition the selection rule, the transition will take place. And the Laporte selection rule or the orbital selection rule or the symmetry selection rule, parity selection rule, they are known in different names. That shows the secondary quantum number, 2-degree quantum number or azimuthal quantum number, delta L should be plus minus 1. This rule has been formulated not abruptly or arbitrarily. There are certain mathematical calculations after which this has been obtained. So that is obviously not the time to discuss those theories, but you can remember these selection rules. Two selection rules: spin is delta S is equal to 0, and Laporte selection rule is delta L is equal to plus minus 1. Suppose I am talking about a transition. Say the example is if I take chromium 3. Suppose titanium 3, I am talking about a D1 system. Titanium 3 plus is a D1 system. So one electron is there. Now when the transition takes place, what happens? When the transition takes place, then this electron goes there. So this is this. Now, if you want to calculate the value of total spin, here is half. Each electron contributes half. So here is half and here is also half. So what is the value of delta S? That is 0. So this is an spin allowed transition. That's why titanium 3 plus shows a pink color. If I take a D2 electronic system, suppose vanadium 3 plus. Vanadium 3 plus is also colorful. Then in the vanadium 3 plus or the D2 electronic system, after the transition, the electronic configuration will be this. There is one electron, here is one electron, and here is one electron. So before the transition, it was half plus half, and after the transition also it is half plus half. So delta S is again 0. For chromium 3 plus, one electron is added here, and it is like this. Again plus half and plus half. So for D1 to D3 system, it remains same. Say for the D4 system. Okay, for the D4 system, say it was like this. So after the transition, it will be like this. Again, it is plus half and it is also plus half. So delta is 0. So for high spin, D1 to D4, all of them are spin allowed. Okay, so they are colored. They are highly colored. Now, if I go to the D5 system, initially was like this, and after the transition, it will be like this. Now you see the changes. Initially, it was again plus half, but after it is how many total number of unpaired electrons, 1, 2, 3. So it has been reduced. That means I am erasing this part. How many? 1, 2, 3. 1, 2. Now you see the value has changed. Now delta S is equal to 5 by 2 minus 3 by 2 is equal to 1. That means it is delta S is no, it has a non-zero value. Therefore, this transition is not possible according to spin selection rule. So if I say that D5 system, but the condition is that D5 high spin, so that all the 5 orbitals before the transition are singly occupied. In that case, the transition is not allowed. In that case, transition is not allowed. So what is the example? Example for this is MnF2.6H2O. This molecule, it has Mn in +2 oxidation state, and fluoride is a very weak field ligand. That's why it is almost colorless. Very light, faint pink color is observed. Faint pink. That means colorless to faint pink color. Okay, colorless to faint pink color is observed for MnF2.6H2O as it is a high spin D5 system. So in this way, we can accommodate the role of selection rule in the color of the coordination complex. Whatever I have discussed till now, that is all of them for spin selection rule. And what is Laporte selection rule? Laporte selection rule says that delta L should be ±1. What does it mean? It means that the transition should take place between different orbitals, that is S to P, P to D, D to F, or vice versa. Like this. Okay, but no transition is possible to S to S or P to P or D to D. These are prohibited because in those cases the delta L is 0. What is the relation between S, P, D, F and L? We know that the value of L is equal to, we can put the value of L, okay, L and the orbital. When the value of L is 0, that is the S orbital. When the value of L is equal to 1, that is a p orbital. When the value of 2, 3, sp, d, f, in this way, 0, 1, 2, 3, sp, d, f. When we consider the atomic structure part, it shows that these are the relations between the secondary quantum number and the orbitals. So it shows that your transition should take place between different orbitals which are consecutive in nature. That means with a difference of delta L is equal to ±1. Okay, so that's why the transition between the same orbitals do not take place. So this is the, so in this way we can see whatever transitions, electronic transitions has been discussed here, all of them are DD transition. Okay, so that means the transition is taking place from one d orbital to another d orbital. But Laporte selection rule emphasizes that these transition between the same orbitals are prohibited. That means all the DD transitions are Laporte forbidden. So whatever the color is obtained, that is due to the spin allowed transition, because all the DD transitions are Laporte forbidden transition. Okay. Now lastly, I would like to mention some molecules where there is no electrons in the d orbitals, but still very much colorful in nature. Suppose we can think about the molecule of say KMnO4. KMnO4 manganese has 7 plus oxidation state, so it is a D0 system. Then why it is so highly colored? Okay, because of the not because of the minus not because of the DD transition, rather a ligand to metal charge transfer transition takes place, LMCT transition, where the negative charge over the oxygen or on all the four, because this is a resonating structure, all the oxygen atoms contains that minus charge, and that minus charge is shifted at different are shifted from here to manganese 7 plus. So 4 different transitions are observed, and we get a very highly violet color of this molecule. And as is observed, like say, they are like this. And the last one, say this is 400 nanometer, and this is 200 nanometer, and this is say 800 nanometer. So this region, the tail of one of the charge transfer transition, that is this part, falls under the visible region, which gives rise to the color of the molecule. So this is, I think, the first module. We can wrap it up here. Now, I can open the I'll share some questions. I'm stopping the sharing here of this file. So, is it visible, the module 1 tutorial sheet? Solve question with model answers.
Yes, sir.
Okay, so you can see how the what are the questions. Differentiate between double salt and the coordination compound. We have discussed this one. Difference between ferrous sulfate, ferrous ammonium sulfate, and butyramine sulfate. Here it has shown the one important example will be how to find out the primary and secondary valency of say copper in the second molecule in the coordination complex. Okay, what is the primary valency? Copper's charge, that is 2. And the secondary valency is the number of the ligands surrounding attaching with the copper, that is 4. Okay. What are ligands? Example of different types of ligands and how they are classified. Ambidextrous ligands, which can simultaneously be added from which can be added from either of the two donor sites. Okay, in one case like thiocyanate or isothiocyanate, it can be attached either with nitrogen or with sulfur. Nomenclature, leave this. There will be no naming. That is not under consideration. Now look here. These are very simple calculation of the oxidation state. This will help you to understand the primary valency. Okay, in all these examples. Main postulates and significance of Wagner's theory, we have discussed this. And from here, the important part is how much amount of silver chloride is precipitated. Just say like in this example, from here, when we talk about the Wagner's theory, this is one inner orbital and outer orbital complex. We have discussed that for the inner orbital and outer orbital, when the inner orbital will come when the ligand is very high field or a strong field ligand, then the inner d orbitals are participating. So it is a inner orbital complex, and when the ligand is a weak field like water, the outer d orbital will be participating. So it is an outer field, outer orbital complex. Now explaining bonding in chromium NH3O6 complex having valence bond theory. Just the same example repeated here. Same with carbon monoxide. Just you need to understand if it is a strong field ligand, then it will form the inner orbital, and if it is a weak field ligand, then it will form outer orbital. Okay. Some example of this electronic transition, what the determination of lambda or the tetrahedral splitting, that delta E, whatever I have written there, delta here, delta T is the tetrahedral splitting is the Hc by lambda. Just putting the values of Planck's constant, velocity of light, and lambda is given here 545 nanometer. So you just put that in the SI unit. Taking all these in SI unit, you get the value of the tetrahedral splitting like this. Calculate the total pairing energy. You can choose it by filling up the electrons. Calculate the CFSE value. Just you need to put the first for cyanide. Cyanide will give you a it is a strong field ligand, so a low spin one. Okay, then its configuration will be all of them will be here in the T26 electronic configuration. So -4 into 6, that is -24, that is -2.4 delta. But in that case, you need to pair up the electrons. So the pairing energy is need to be added here. So in this way, but in cobalt Cl6 -4, cobalt Cl6 -4, there is no pairing energy. So that's why it is only -0.8 delta value. Calculate the magnetic moment of these things. I think first I have discussed in how you can calculate the magnetic moment effectively. First you calculate the oxidation state of the central metal ion, then find the number of unpaired electrons by filling in the crystal field, and from there use the equation √n into n+2, and you will get this. Crystal field splitting diagram of the d orbital, assuming different. What is this? You do not need this one. This was assuming for a linear MX2. It is not required. It will study only the tetrahedral, octahedral, and square planar. For the color, it has already been discussed. I think these are gentler distortion has also been discussed in the last class. Then elaborate way. Now the question will again may come from the normal or spinal, normal or inverse spinal. We have seen that when the inverse spinal is appearing, it may also be helpful if you are provided with the lambda, that is the occupancy factor of the tetrahedral void space. If that is 0.5, that is that is an inverse spinal, and if it is 0, then that is a normal spinal. But that has come from the by observing the relative energies obtained or the stabilization energies obtained if that metal ion enters into the octahedral or the tetrahedral hole. Explain the structure, dimeric structure of copper 2 acetate monohydrate. I have discussed these things and why their bond is and why their magnetic moment is less. Why the complex contains the D2 electronic configuration usually colorless. What I have discussed for the Mn2 D5, the same is the reason. For D10 also, all the orbitals are filled up, no extra CFAC, and there is no gap, there is no vacant orbital for the transition of electron, so no electronic transition takes place. However, for the digital system like MnO4- and dichromate, why the colors appear, that is due to the ligand to metal charge transfer. We have discussed that one. Lambert-Beer's law is given by the equation A is equal to log 10 I0 by I is equal to epsilon CL. Now, depending upon the at a particular wavelength, this epsilon the molar absorptivity is constant, and L is the path length of the solution. So, at a particular wavelength, this epsilon and L is constant. So, at a particular wavelength, the absorbance is directly proportional to concentration. So, with the increase in concentration, the absorbance also increases. What is charge transfer phenomena in complex? I have discussed this. What are the spin forbidden and spin allowed transitions? We have also discussed this. MnH2 whole 6,2 plus is colorless, while MnO4 minus is intensely colored. It has been discussed. Importance of CFAC in spinal compound, just to check on moving into that void space. If it gains some extra CFAC, then that spinal is followed, whether it is a normal or an inverse one. Similarly, vanadate is colorless, but chromate is colorful. Okay, in the first case, both of them are digital system, but in the second case, there is the extent area. All of them have the same, but it depends upon the charge transfer transitions. Okay, wavelength of the transition increases in the series with permanganate having its charge transfer absorption at the longest wavelength. So actually for permanganate, the charge transfer transition takes place. Some part of it appears in the visible region. That's why it is highly colored. But whereas for chromate, it is also highly yellow colored. That also appears in the visible region, certain tail. But for vanadate, its tail doesn't come in the visible region. It aims in the higher UV region itself. So that's why it is colorless. Okay, these are some other questions. You can also go through these and just the example of some isomerism, isomers, geometrical optical linkage. We have, as we have discussed in my note, you follow that. Okay, and in the note it is given in detail. You can also study from there. Those are only given here. Okay, so I think we have we have completed this part of module 1 with a brief discussion of all the modules, all the materials and all the subtopics of module 1. Okay, so now now it is open for anyone of you. If you have some question, you can do that. So, so anybody, if you have, I have allowed the mic for everyone. So if you have any concern, then please ask. I think you have seen how to download it from the team. Everything is there. You can check it from there. And regarding the module one, if you have any question, please don't hesitate. Ask. Yes, Dr. Amit, are you there? So if your students are if your students have any queries, then you please ask them and ask them to place it right now. Ranjana ma'am from Jaipur, I think. Is there anybody to have any question?
No, sir.
Okay, so I think the matter is very clear to you. Just go through the notes and the tutorial sheets. If you have any further queries, you can also send an email. No problem. So can I finish it here? Okay, so thank you very much. I think you don't have any question right now, but no problem if you can send it also in an email. Okay, so thank you very much for attending the class.
Thank you,
Okay.
sir.
Yes, Anand, please tell.
Sir, all clear.
Okay, thank you. So all the best for your midterm exam.
Yes, sir. Thank you.
Okay, and first two module will come, no third module. Module 1 and module 2 will be the syllabus in the mid semester.
Yes, sir.
Okay.